Let's do graph. My sense is that, by the way, you guys have been exposed a little bit to DFS before, maybe. Okay, so the beginning might be just warm up then, but that's okay. So, so we're going to talk about searching and sorting graphs today. We sorted numbers. Now we're going to sort graphs. We're going to talk about directed graphs in particular. We'll talk about acyclic graph. We'll talk about something called topological sort, cycles, reachability, depth first search, strongly connected components. Many of these words you might have at least heard of before. Okay, good. Okay, so I can't skip definitions. So a graph, right? Actually, we probably had graphs on the homework, so you that must know it by now. But there's vertices, points, there's lines connecting them in between, pairwise connections. Those are edges. You can have like ordered connections, really A going to B, but not necessarily B to A. Those are directed edges, or undirected edges, which are more like mutual connections. Okay, so like Facebook friendships or Twitter follows. Uh, There's different ways to represent a graph. Here are the two most standard ones. Okay, one's called an adjacency list. So for every vertex v, I just say, oh, what are the other vertices that you have an edge to, and it'll just list them out. Oh, you have one edge to that one edge to that one edge to that one. Okay, now it'll be like fairly space efficient because you really only need space proportional to the number of edges in the graph because it just lists and lists and lists. And the other standard one is something called an adjacency matrix. So I'm just going to allocate a big, if there's n vertices, n by n table. And if it's an unweighted graph, I'll just put a 1 in the entry if there's an edge from A to B. Then the entry AB will have a 1. And if there's no edge, I'll put a 0 there. Maybe if there's some kind of like edge lengths or some kind of like quantity associated with the edges, I'll put that quantity instead of 1. Okay? So the con is like, okay, if the graph is sparse, it doesn't have that many edges. The n by n, you're allocating a lot of space for, it's going to be mostly zeros, right? Which you could have kind of skipped. On the flip side, you can just say, if you wanted to know, is there an edge from A to B, you can just look it up in a table in one step. Yeah. And then there's like, various hybrid versions. Like for an adjacency list, if I listed the neighbors in sorted order and I wanted to know if you have an edge to such and such, I can binary search for that vertex or something, save a little time compared to scanning the whole list. In general, these aren't really that big a deal. Okay. So good. All right. So let's get to the more fun parts. So let's talk first about DAGs. All right. So DAG stands for directed acyclic graph. Acyclic is the opposite of cyclic, I guess. So there's no cycles in the graph. Okay. So if you look at these vertices, any vertex, I'm here. I can't get back to here by some path in the graph. Okay. All the edges in this case are going from left to right, so you can't really get back. Okay. So is there anything down here? Nope. Okay, so why are DAGs interesting, or where might they occur? So a very common place is something like a logical circuit. Okay, so you have expressions like and or and not, these Boolean expressions. And you create these DAGs where at the bottom you have some nodes that represent the input. And you think about these as like Boolean values propagating through the graph. Okay, so like for this formula here, if this was like true and this was like false or something, x1 is true and x2 is false, then, as you kind of propagate, maybe I go up this edge and this is a not. That symbol is supposed to represent a negation. So this true becomes false. This false becomes true. And then you start having these ors, right? So like false or false is false. True or true is true. Yeah, and you keep, and that'll come out, I guess, to false. Okay. And I guess this is supposed to be XOR. Seems like that's XOR, right? Okay. A more complicated one that took me a little bit longer is addition, okay, or kind of verifying addition. So I'm just adding up 2 bits and it produces a 2-bit output. So I have x1, x2, x3, x4. and I want to make a circuit that returns true only if x1 plus x2 is equal to that two-bit number x3, x4. Okay, so this is maybe harder to verify or see how I came up with it, but this will be a circuit for addition. All right, so that would be some circuits in the wild, or DAGs in the wild. And right, so we have these logical gates, and presumably you may have seen some of these before. AND gates, OR gates, or NOT gates. Okay, so they're going to take the input and apply the corresponding Boolean operation to it. Here I think I've kept this simple and made sure that each node has at most 2 children coming in, but certainly like an AND can have lots of inputs coming in. You'll take the AND of all 5 values or whatever. Okay, good. All right, so more systematically, right? Imagine you're trying to make an algorithm to evaluate a circuit. So there's some values plugged in for x1, x2, x3, x4. Like, just as an English description, how would you evaluate a circuit? So it's all kind of like written down in maybe some adjacency list format. You know, you have the nodes and you have the edges, and I also write down this node is an AND operation, this AND. You know, so you have the information. It's not too hard to access. So you start with these 4 values, right? X1, X2, X3, X4. They're like filled in with some values. That's your input. And my goal is to compute the answer, what the circuit evaluates to. Yeah. Yeah, so I might do like this one first, right? Because I have X1 and X2. And then, yes, you said next layer. Layer was like a keyword, right? And so that might be the third one I do, right? And so in this picture, we're kind of going what direction? Up, okay. I'm getting comments on YouTube that they want to hear everyone. I don't know what to say about this. Okay. Like, okay. Uh, right, but you go from bottom up. Okay? So that's natural thing to do. One at a time from bottom up. Okay. So, okay. And at some level, you know that to evaluate, this AND, I have to make sure I've evaluated everything that has an edge going into it first, right? Those are the inputs. Okay. So the order in which I want to evaluate things a fancy word would be topological order. So if I have these edges, I think of all of them as less than equal signs. Edge from A to B means A is less than equal to B, right? And that will define a partial order because there's no cycles, right? If you had like A less than equal B, B is less than equal C, C less than equal A, that'll give you a cycle. But here we don't have any cycles, so it's okay. So that'll give you a partial order in the graph. So some things, if A goes to B goes to C, then transitively A will be less than equal to C. Okay, but if there's no path from A to C or C to A, then one could be before the other. Who knows? Yeah. Oh. Okay. So you have a partial ordering. There's some that you know are less than equal to some others. Yeah. Oh, no good reason. This could have been less than. Yeah. I think maybe less than equal will make more sense if we allow for cycles, in which case, like I can think of all of them being equivalent if they're connected. So, which hasn't shown up yet. But yeah, it's some precedence, some order. Okay. And so a topological ordering of V, yeah, I think less than equal will become more useful later. So it's good choice, but it's not too important at the moment. Will be any listing of the vertices that's consistent with the edges. Okay. So like, okay, let's take our circuit. I'm just going to have you tell me which one can be listed first if I wanted to build a topological order. And I'm just going to enumerate the circuit. And just say it out loud. X1, okay, 1, and then X2, and then, okay, and then, okay, and then, like this. And then, oh, did I just do this for the other? Okay. All right. So not much. Okay. So we already kind of did this. Okay. So that's giving you some kind of topological ordering. And if you drew it out, as I apparently did, right? Uh, this should be listing left to right in the exact same order we did, right? And suppose you had that topological ordering, right? Imagine you're now trying to write this algorithm that actually evaluates a circuit. And suppose you had a black box that computes a topological ordering. That would be kind of convenient, right? A graph is a pretty generic data structure. I mean, yeah, data structure, and I just want to get a topological ordering. Once I have this listed down, it'd be very easy to write the algorithm that goes through this list in order, right? At some level, I don't have to deal with any of the graph anymore. I just go through from left to right and evaluate these things in order. So one way to evaluate a circuit is just explicitly compute a topological order, get listed down, and you just have to loop through. Okay. Oh, rats. Okay. Well, I was going to ask, how would you topologically sort a graph? And the answer was supposed to be hidden. But given that it's written there, okay, here's maybe one way you could do it. Okay. And in some way, I think the way we intuitively just did it. We just figure out what comes first, which would be any vertex that doesn't have anything coming into it. That's called a source. Okay? So I might say, okay, this is number one, right? And then I can erase these. I've already got rid of it. So I'm really just worried about which of the remaining vertices has something coming in the out of the remaining graph. This will be 2. Okay, mark that off. Then we have some choices. This could be 3, for example. We mark that off. This could be 4. We mark that off. This could be 5. We mark that off. Right? We have lots of choices, but we just keep iteratively finding a source in the remaining graph. Okay, I think you get the idea. Okay, right? So that's one relatively simple algorithm. And it wouldn't be so tough to turn this into some kind of relatively fast code. Okay? So conceptually, I'll just start with an empty list, and I'll look for a source. I find a source, I add it to the list, I remove it from the graph. Look for a source, add it to the list, you know. Okay, now how do you actually do this fast? I mean, if you went through the graph over and over again looking for a source, it's going to take you like roughly quadratic time, right? Each time I remove a vertex, I have to scan the whole graph. So it'll be like n squared mn or something like this. Okay. But something that you could do that might be easier is you go through once and you figure out every vertex's in degree. How many edges are going into that vertex? There's some tallies, right? And sources will have in degree 0. And I just could keep these tallies in a sorted list. Or I can keep an array. Here's all the vertices, degree 0, degree 1, degree 2, degree 3. There's many ways to really make this concrete. And then I'll just to pick some vertex as degree 0, remove it, put it in my list. And then I have to look at its edges that leave it and update a few other tallies and update my lists. So by just keeping track of in degrees as things get removed, that won't be so hard to do. Okay. So if you do this whole thing and you're reasonably careful, it should take you linear time. Okay, simple enough. Okay, good. Now, okay, so much for topological ordering. Now we'll talk a little bit about searching graphs. Any questions? No questions, great. Okay, here is, I guess, a picture of a graph. What was the point I wanted to make here? Unclear. Okay, so if I am starting at Lawson and I need to figure out how to get to our classroom here, right? And you have some kind of graph, and so forth, right? So any map will give you some kind of graph, and I want to try to see if there's a path from Lawson to get to here that maybe doesn't go through snow or something. So, okay, this is more fun actually. Okay. I don't know what point I was trying to make before. All right, this is what we call the cat maze. Okay. So here's a question of a pathfinding problem. Okay. So I think you can probably read the rules, but you have these cats and you're jumping from cat to cat to cat. Okay. Some cats are facing you, they have eyes. Some cats aren't facing you, they don't have eyes. Okay. And so you start at the top left with that yellow cat that's facing you, and you can only move from a cat that's face forward to a cat that's not face forward to a cat that's face forward to a cat that's not face forward, but they have to be touching each other, like in the picture. Yeah. So the question is there a cat path in a cat maze from start to end? This might take some time. No? For this one. Yeah, you need to find a cat maze. One person has already decided there's no cat maze. Oh, sorry, cat path in the cat maze. There isn't any? No, no, no. I don't know. All right, who thinks there's a path? Who thinks there isn't a path? Okay, how? It's always hard to figure out how do you conclude there's no path besides like you stared at it and gave up. Started from the end, so you probably went to here. Okay, so you can't go there, so you can't go here. Uh-huh. What? No. Light blue. Oh, here. Okay. Okay, and you got stuck. I see. So maybe you all did something like this, and you're like, okay, now I'm stuck, and you conclude it's impossible. Okay. Did anyone find one yet? Damn it. Yeah? Okay, so that's the answer to the cat puzzle. Okay, so there's a blue cat in the middle. Okay, yeah. Yeah, did I cheat? Yes, I did. But I think these are all touching each other. Uh, which yellow one and which blue one? Towards the end? Uh, this one? Well, they're right next to each other. Oh, yeah. That's the missing cat. That's a cat in the middle because it has no eyes. Okay. All right. So good. So you've all learned DFS, but at least you hadn't seen this problem before. Cat DFS. Okay. All right. So in general, when there's less ambiguity about the vertices and edges, you're facing some problem like this, right? I give you a graph. I start with S, and I say, can S reach the rest of the graph? Right? Typical kind of map navigating problem. All right. So how about this one? There's no secret cats in this one. Can S reach all the other vertices in the graph? Is there a way to get to all the other vertices? Okay, I see some head shaking, which most countries means no, and sometimes. So if not, which ones cannot be reached? Yeah, go ahead. Oh no, no. So can S reach starting from here? Not everyone. Yeah, yeah, yeah. It is true that anyone who's a sync cannot reach anyone else. That's true. That's true. But S, who can S reach and not reach? Yeah, this one. There's this edge. This one. If you're just looking for a vertex that's in degree zero, I guarantee they all have in degree at least one. Yeah. All right. Right. So these three vertices in the middle, I put them in a cycle so that they won't have in degree zero. But as a collection, they have no other edges going in. Okay, so you can't reach those vertices in the middle. Okay, good. So so our goal is to try to figure out an algorithm to do this systematically for us. Yeah, and this was only like I don't know, 12 vertices or something, and it's not that easy. Okay, good. And then maybe like one perspective to keep in mind is that we always think of like graphs and mazes from like a bird's eye point of view where you can see the whole thing globally, right? Which at some level you can do, but an algorithm is always kind of taking one step at a time and doing one piece of information at a time. So I feel like an algorithm is always really more working in like Google Maps or Street View kind of thing, right? Like it's sort of really navigating. It's really kind of on the inside of the maze trying to explore the whole thing. Computers can't just like take such an easy bird's eye view in general, LLMs aside. Okay. So, okay. So as a warm up, I know you guys know what the eventual algorithm will be, but still, let's try making just a generic recursive algorithm. Okay. Where I'm just trying to figure out if I can get from S to T. Okay. So what might be a reasonable sentence, a recursive spec? If you're doing this from first principles. Yeah, so this one we'll just do something that returns true or false. True if S can reach T, false if not. Okay. And again, from first principles, how might we implement it? So down below, I've already started out recursive search from S to T. Yeah. If S is T, we should return true. I guess the next line must be if S is not T. Oh, no, it wasn't. Okay. All right. So if it's not equal to T, then what would you do? Yeah. Yeah, so okay, if S is not T, then if I can get there, I must take another edge. So let me loop through all the edges leaving S, going to various neighbors V, and and recursively call it, right? If one of those calls can reach T, then the answer is true. And what if they all fail? Oh, return false, right? Right. So it feels like this is sort of a very straightforward thing. Uh, Either S is equal to T, and I'm good. Yeah. Right. So yeah. So what's wrong with this argument, right? If I want to try to argue, uh, about correctness, right? Okay. So I can imagine, someone writing down if s can reach t and s is not equal to t, then it must go through some other vertex v, and recursively, recursive vt will get me the answer, right? Uh, but of course, I think you've all kind of implicitly pointed this out. What about something like this, right? A simple setup like this. S can never actually reach t, of course, and the algorithm will never terminate, right? So what's wrong? Yeah, so there's some problem with our induction argument. We're not really making things smaller. You get stuck in loops and things like this, right? So that's one of the tricky things about graphs is you're roughly dealing with these cyclic structures, and it's not so easy. So, okay, good. Right, so recursion is not enough. Okay, we're gonna have to do something, update some kind of state. Yeah. Yeah. Okay, let me work up there like a teacher. Okay. Uh, okay, let's say that you're 10 years old, you're at Chevy's, you get one of these placemats with a maze on it, right? And how would you like literally try to do this maze? You try every path, but like physically what would you do? You would draw with a crayon in particular, right? So, you would start marking, where you're going, where you've been, and without doing that, it might be very, very hard to solve a maze, right? So this is just some Hansel and Gretel kind of thing, right? We're just going to do some idea like leaving breadcrumbs where we went to make sure we don't repeat, as you all know. Okay, so this is the same idea as filling out a table, but presented a little bit differently. Okay, and you've all, of course, seen this algorithm before. So when I visit a vertex for the first time, I'm going to mark it and say, I was here, and you'll search the neighbors, right? And next time you come back to it, if it's already marked, you say, I've already explored this vertex. I don't need to check it again. Okay, and that's the only difference. We're just going to add this mark. Okay, so I guess this is set up for some kind of demo. So if you're actually starting from S, right, you might search here and you mark it for the first time. And then you search here, you mark it for the first time, you search here, you mark it for the first time, you search here, you mark it for the first time. Oops, you keep going. You only backtrack when you run out. You search here, you mark it for the first time. You search here, you mark it for the first time. You search here, you mark it for the first time. You back out. You back out. You back out. I hope I don't miss something. You back out. Now you go here. You mark it for the first time. You back out. You back out. You go here, but you've already been here, so you can back out right away. You back out. Then you go here. You mark it off. You haven't been here before. Now you go here to this vertex in the middle, and you've already been here. So you don't need to explore it again. You back out. You back out. You go over here. Boom. You go here. You've already been here. Back out. You go here. You've already been here. You back out. You back out. And there's no more edges left for S. Okay. And indeed, the unmarked vertices is that triangle in the middle, just like we hoped. Okay, good. So let's prove this works. Okay, I want to make two claims. One is that it's going to run in linear time. And the second is it's really going to visit all the vertices reachable from V. Right? You might be afraid that, oh, marking is somehow going to cut off some options in the future. Okay, so, and maybe this is all kind of clear, in which case the exercise is how do we just get it down in a clear fashion, right? Still articulating it, something that might seem obvious, is a challenge. Okay, so how can I argue first the running time is very good? Doesn't have to be complicated. Yeah. Yes, but why? Some of that's a claim in the running time. Yeah, I mean, I think that's basically right. Here's how I articulated it, because I just want to write in some clear way, it's easy to read off and say, oh, of course. So we only traverse an edge UV after marking U. Yeah. And we mark each vertex once. That's also clear from the algorithm. So you only traverse each edge once, right? I think that's it. Okay. So you only traverse an edge after marking a vertex. You only mark each vertex once. I think both of those lines are immediate from the code. Okay. Right. So nice and clean, no room for ambiguity. All right. Let's do the slightly more involved claim, right? Which I'm sure you've all seen before. The claim is that, if I run depth first search from V, I'm really going to explore every vertex that's reachable from V. Okay? And there's probably different ways to do it, but here's how I set it up. So, um, let's say I'm starting from V, okay? And and there's some other vertex W, and I'm promised that V can reach W. Okay? But suppose by contradiction I don't visit W in the algorithm. There's something wrong with the algorithm. Okay, so let's set up two sets of vertices. So I'm calling A a set of all vertices that do get marked by the algorithm and are visited, and B to be all the other vertices. Okay? And I assume that W is reachable from V, right? But by contradiction, W wasn't marked, so it's in the set B. Why did I choose B? That sounds like V. I don't know. Okay, so, all right, so there must be some path. Let me draw a little differently. Okay, there must be some path, right, from V to W or some walk. That's fine. Now, okay, so what I want to do is I want to articulate something that might seem obvious to you, but I just want to figure out how to write it down. Okay, so does anyone want to try to propose, I guess, the final sentence of the proof? It's the longest sentence, but yeah. Okay, so yeah, if the walk crosses over a river, then there must be a bridge, right? An edge, right? So there's some edge that's going from some vertex A that gets marked to some vertex B that's not marked. Okay, and then keep going. Yeah, so if you visit A, right, and you mark A, then you're going to traverse every edge, including A to B, right? So this would be A, B, and you're going to call DFS on B. Okay. So did I write it down? I didn't write it down. Well, that's okay. Um, so B will have to get marked, but B was supposedly not marked, and that's your contradiction. Okay, so you just set up the thing. Okay, there must be some path. It starts on one side, ends to the other. There must be some edge, right? You kind of pinpoint the part where there's some issue. Say, okay, I know that A got marked. That means the edge must have got traversed. B must have got marked. But you said that B didn't get marked. Okay, there's our contradiction. Yeah, I think nothing too surprising. It's just how do we get it down clearly is really the lesson point. Okay, good. So much for that. And I guess you've all seen this before, so it shouldn't be too surprising. So it runs fast and it'll visit everyone. Okay, and maybe more precisely, this will be a slightly more useful sentence for later. DFSV will not return until all vertices reachable from V have been marked. Sort of like a more concrete way to say it visits everyone. All right, good. What's the point of this? No one knows. Okay, All right, so now let's get to I think the most interesting part of the lecture. Okay, sorting graphs. Okay, good. All right, so beginning we did, topological sort. You remove sources one at a time and you get the topological order or a topological order. Okay. So on the other hand, we just showed that if I call DFS from any starting vertex and even consider any intermediate vertex V, okay, between the time that V is marked and DFS of V exits, okay, DFS will only search the vertices that are reachable from V. Okay, I think that's kind of given from looking at the code. Okay, so here's our lemma. Okay, so imagine you run DFS from some other vertex, and now focus on two other vertices in the middle of your graph, V and W. And suppose V can reach W, but W cannot reach V. Okay, the claim is no matter where you start and all that stuff, any DFS that explores and marks V and W will finish DFS W before DFS of V. Okay, so the claim is that no matter where you start, if V and W both get explored, DFS W will have to finish before DFS of V. Yeah, I think that's true, but let's figure out how to, like to say one more, I think is not quite strong enough to really imply this statement, but I think it's absolutely the right idea. So I wanted to figure out how to take one more and flesh it out, that the phrase one more. Like in your mind, like if I run DFS from V, it should reach W or something, right? So let's just figure out how to break this out, break it down on paper. Okay, so let's try to prove this. Okay. And I guess the way I set it up is I broke it up into two cases, right? So let's say you want to prove, what are like some natural cases? I'm not sure if this is guessable. Yeah. Yeah, kind of. Did you have an alternative? Which one is reached first, I think is a little bit cleaner. It's possible that yours also would go through, and I just wasn't prepared for it, right? But one way or another, the algorithm is going to visit V first or W first, right? That's sort of very unambiguous and very clean. So we can just analyze these two cases, right? Okay, so let's say that DFS marks V first. I want to argue that it'll mark and finish DFSW before. Yeah, I mean, I think this was just some sentence we just had, right? Effectively what we've already proved. The DFSV will make sure it visits, reaches, and finishes everyone before backtracking back out. Okay? And then what happens if it marks W first? Yeah, I think there should be a V. Yeah, I agree. Okay, let's say DFS marks W first. Yeah, so we already argued or pointed out that DFS will finish exactly the vertices reachable from that vertex before backing out, and nobody else. It's not going to reach some other vertex. So, uh, yeah, it won't reach V. Okay, so that's it. Okay, nothing too complicated. I think maybe the only important step was to break it down cleanly into those two cases, and then filling it in was not so bad. Okay. All right, so that's not too bad. Okay. All right, now with that in mind, uh, imagine the following. I run DFS, okay? And as I'm about to finish processing a vertex, I marked it, I explored it, went in, went out, went in, went out, and now I'm going to back out of this vertex V. I'm going to print it out to some list. Okay, we call that the post DFS order because it's happening at the end of visiting each vertex. Okay. All right. So what we want to do is we want to study some properties of this order. Okay. All right. So let's say I ran this on a DAG, just as a warm-up. Okay. First I take two vertices, and let's say U can reach V. Then V can't reach U because, yeah, because we're in a DAG. Okay. Now, so that means that that based on that lemma we just did, DFS will always print V before U. Okay. So if you print it out in order, okay, on a DAG, okay, so I print out the order, and what I just said was that if U can reach V, then V gets printed out before U. That means if I list out the vertices and I drew the edges, they'd all have to go backwards up the list. Okay, whatever the edges are. Okay, so good. That means that if I want to get a topological order, oh, I forgot something. Yeah, okay, so the point is this is the reverse of a topological order. So if I want to get a topological order of the graph, what could we do? Yeah. Yeah, I could run it and reverse it. What's another way I can do it? I can also reverse all the edges in the graph and run DFS. Either would work. Okay. You know when we start, right? Oh, the rain? Yeah. Okay. um, okay, so you can run DFS and you can reverse your output or reverse your input, and you can get another topological order. Okay, so now we have two algorithms. Good. All right. Good. Sorry, I feel like this lecture is not. Anyway. Okay, let me introduce some. Yeah. So the topological order is not unique. Oh, yeah. Okay, so I should be a little bit more careful then. So you could have run DFS from the middle of the graph. It doesn't have to be from a source, right? And you'll reach some of the vertices, and some of the vertices won't get reached. They won't get printed. Okay. So what we can do is we need to add some kind of outer loop to make sure we visit everyone, right? So sometimes we just call this a driver. It just wraps around things. So for every vertex V, uh, I'll call post DFS on V. If V is already marked, then it'll just, not do anything. Okay. So sort of no matter how we choose sort of those initial nodes of our DFS search, this printout will still work. Yeah, I didn't really pause on it either. And one way to see that, this is not that big a deal is, okay, imagine you have some kind of graph, like whatever, right? And your driver is kind of picking these vertices in some arbitrary order. Okay, and then you might be a little bit confused. Oh, could there be a bad order? But one way to think about this, it's as if I had added a magical source node, my own source node, as an auxiliary node to the graph, and added an edge to every vertex. Okay, so this S star, if I had added an auxiliary node to the graph and connected it to every vertex in the graph and ran DFS from that source vertex, that's sort of like what we're used to, right? Like one vertex can reach everyone, it's going to print out everyone, and that we feel very comfortable with. But it's doing the exact same thing as this post DFS driver. It's just picking vertices in some order and calling DFS. So yeah, this isn't going to create any headache for us that we have this outer loop. It's as if I had it one vertex that could reach everyone. Okay, it's an easy way to think about it. Okay, good, good. Okay, all right, let's keep going. Okay, so for simplicity, we've been focusing on situations without cycle. Let's bring some cycles in. Okay, so I'll tell you, say two vertices are strongly connected if A can reach B and B can reach A. Okay, not just by edges, by various different walks. Okay, and a graph is strongly connected if every pair can reach every pair, or every vertex can reach every vertex. Okay, so in fancy speak, the strongly connected sets of vertices, A can reach B, B can reach A, they form an equivalence class. What does that mean? That means if A and B is strongly connected, and B and C is strongly connected, then A and C is strongly connected. I think that's the definition of equivalence class, but in any case, it's just a word, right? So, um, okay, which means that like the equivalence classes will partition your sets of vertices. Each, right? I look at A and its equivalence set, Okay, but we need to prove this is true. This is still a claim. Maybe it's obvious. Maybe it won't be hard to prove. Okay, so I want to claim that if A is strongly connected to B and B is strongly connected to C, then A and C are strongly connected. Yeah. Yeah, okay, so if U can somehow reach V, and V can somehow reach W, and W can somehow reach V, and V can somehow reach U. Okay, that's all we know going in. Then I know that U can reach W by just concatenating these paths. And I know that W can reach U by concatenating these paths. Okay? And that's it. Nothing simple. I mean, nothing complicated. Everything's simple. Okay. So an equivalence class, like a bunch of these vertices that are strongly connected to each other, is sometimes called a strongly connected component. And when we talk about graphs, right? So here I've tried to highlight in different colors the strongly connected components, right? Like that triangle we found in the middle, that's a cycle. They can all reach each other, just going around the cycle, strongly connected. I guess we have another triangle on the left in purple. That yellow, I guess if you went through it carefully, you'll see that they can all reach each other. And those two sync vertices, they can't reach anyone. No one else can reach it. So they make singleton equivalence classes. They're just by themselves. Okay, and that partitions all the vertices in the graph. Okay, good. So our next challenge is to try to find all the strongly connected components algorithmically, right? I just want one algorithm that gets all of them for us. It groups the vertices for us. Okay, I think this is the most ambitious thing we've done so far in this class. So, okay, let's try a baby step. Suppose I have a vertex V, and I just want to find the strongly connected component of V. Okay, so all the vertices it can reach and it can reach it. How can I do that? Okay, so I can uh, do something like this where okay, so it was a little bit vague, but you said you can traverse from V until you get back to V, and whenever you find a cycle, so you just do DFS until you get back to it. Um, that is not clear to me at work. So for example, okay, so the question is, can you just run DFS from V and whenever you like notice a back edge, you have like a cycle? Okay, so I can imagine something like this. So I have V And I have some cycle like this, so all of these will be in a strongly connected component. But from here, I have another cycle like this. So let me draw some, or let me do it a little differently. Some cycle like this. Okay, so imagine these are all like little edges getting added up to each other. Okay, but you might not notice in your algorithm that this, because there's no back edge from here all the way back to V. Okay, so somehow keep looking for back edges, keep finding. It's true that when you find a cycle, they're somehow in some connected component together. So that's not a false negative, that's a true positive. But I'm worried about the false negatives. It's hard to make sure we comprehensively get everything. Plus, once I start being more careful about, well, there's another cycle over there, and that's part of this, and that's part of this, and it starts to get maybe slower too, right? Okay, but yeah, no, okay. So can we just fix this with another DFS, basically, right? Okay, but then okay, so I'm just going to chain a bunch of these together, right? And now, okay, so oh, I get some cycle, but there's some other cycle hanging off. Can't I run another DFS to try to get that one, that one, that one, that one? Sure, but now you're running a bunch of DFSs, right? Maybe these are all like 3 nodes each. So now there's like n over 3 cycles. Now you're running n DFSs. And that's only like one counterexample I came up with. We still haven't necessarily found something that's like clearly works. It may work. It's not clearly wrong, but it's not clearly working. Yeah. Yeah, but it seems to get tricky. Yeah, but it's sort of similar. I don't know. You run here and you go here. You figure out this. Yeah, is that yeah? So, but these are all algorithms that form like, can you somehow hack DFS? Start running DFS, but then you find a backlink and you try to update some data, saying, oh, these are all connected, and somehow you have to probably retraverse your cycle and say, oh, they're all together, because you have to backtrack your path. Like, what are the things you found between your back edge and right? But these are all solutions of the form. Let's take DFS. I know a back edge designates a cycle that I think these are all based on. And can I kind of go backwards through the cycle and say, oh, they're all together and mark them all together? Certainly they are in a strongly connected component, and then somehow propagate that up if I find another cycle, another back edge, right? And that may be possible. I'm not saying it's impossible, but it seems complicated, right? And by now, I have like, small brain. I like small ideas. Yeah. Ah, okay. So okay, that idea was like, well, if I'm not mistaken. So one idea is let me run DFS from V, find everyone that V can reach, which could be from post DFS or, but you can just run DFS from V and find everyone you mark. And then for each of those vertices, run DFS backwards, right? And see who can get back to V. So everyone who can get back to V, they're in a strongly connected component. Okay, and that will definitely find everyone. And that's pretty simple to describe, right? The other ideas may have worked, but they were getting iffy. Okay, how long would that take in the worst case? Hmm? Yeah, so one DFS down, that's all good. But then each of these vertices you reach, you have to run another DFS. There could be n of them. So you're looking at like m times n times. Let's say m's at least n to make things simple. Okay, so this is a good algorithm, but you can do faster. The first step's correct. I'll run DFS from V, find everyone that V can reach. Ah, okay. Okay, so I thought I wrote this down. Here it is. Okay. I'll run DFS from V. Okay. Now I get everyone that V can reach. I want to get everyone who can reach V. Let's run DFS from V in the reverse graph. Okay. That means uh, so if I reverse all the edges and I run DFS, it's going to be all the vertices V can reach in the reverse graph, but that means those are vertices that can reach V in the original graph, right? And that's only one more DFS, okay? Any of the vertices that get marked in both passes, they're going to be a strongly connected component, right? And this algorithm is obviously correct, obviously takes m plus n time, right? This is a big theme, okay? Sometimes, or almost all the time in this class, don't change the algorithm, okay? Change the graph. Understand what the algorithm does on a graph, and then change the graph. You could have rewritten DFS to look at the edges backwards along the way, right? Like hack DFS to effectively do DFS in a reverse graph. Or you can say, I already know everything there is to know about DFS, and if I just change the input, I understand how it works on the changed input. Because if you change the algorithm, you have to reprove everything. Like some of these ideas about trying to collapse cycles along the way, they might have worked, but at the very least, it's going to be tough to prove. Plus the running time, we're obviously in a world of hurt. Yeah. Oh, how do I take the intersection in m plus n time? Okay. Yeah, any ideas? So I have two lists of vertices. I want to get their intersection, m plus n time. Okay, how about this? So as a preliminary step, you can always pre-process the graph and number the vertices from 1 to n. Okay, so imagine the vertices have integer IDs from 1 to n. If they didn't, you could have in the first step renumbered them. So in that case, what might you do? You could do better than sorting. Because sorting will take n log n, right? That's not so great. Tallies in a map? Yeah, what would be the kind of, yeah, give me a specific example of a map, I guess. Make that more concrete. Yeah, I could just make an array of size n, 1, 1, 1, 1, whenever I find them, and then just walk through. Yeah. So, and yeah, we don't, yeah. So that's not so bad. Okay, good. I hadn't really noticed that before, so it's good that you asked. Okay. All right, so simple enough. But the key point here, though, is sometimes thinking about changing the graph, right? And that'll be the solution to many of your homework problems. Okay. All right, so we already went over this, right? So if I run DFS from V, that's m plus n. In the reverse graph, m plus n. I even didn't write the running time for the both because I didn't think much of it. Altogether, it's m plus n. Okay? But it is true, it's non-trivial. Okay. Now, the original question was how to get all the strongly connected components. So if I repeat this from everywhere, we would get what running time? Yeah. Okay, so you get like mn if we assume n's bigger than n. Okay, good. Okay, so the question is, can you do better? Okay. And for some reason, like, I thought this would be a helpful visual cue. Um, okay, so if I had chosen DFS, starting from V here, it's going to visit quite a lot of the graph to eventually figure out that yellow is what I'm looking for, right? Okay. But at some level, like, if I had run it from here, I would visit this part of the graph and like this part of the graph, and that might be in some sense less of the graph I'm searching or something, right? Like if I could have picked any vertex V, which to run DFS from and do this, pull out the strongly connected component of V, which vertex would have been great? Anything besides source and sinks? Yeah. Or like this would have been great if I could pick out a sink vertex, right? So if I knew this was a sink vertex, and I ran DFS from V. What is the point I wanted to make here, actually? One sec. Oh, okay, one sec. Okay. Backtrack a moment. Imagine I didn't say anything. Okay. Suppose I took my graph, okay, I highlighted the strongly connected components, and I contracted it on the right, okay? And that graph on the right has an interesting property. Well, what is it? It's a DAG, because every cycle got contracted. If there was a cycle among the strongly connected components treated as vertices, they would have collapsed into an even bigger strongly connected component, okay? So this graph of strongly connected components, okay, which sometimes we just refer to as like the auxiliary graph of strongly connected components, forms a DAG. Okay, and we're going to try to take advantage of this property. So our current approach, our relatively slow algorithm is pick any vertex, get the strongly connected component, rip it out of the graph. And it can take mn time, okay, if you're not very clever. Well, I want to follow that same high level idea, but get the running time down. So suppose, okay, so in that DAG of strongly connected components, there's well-defined sink components and well-defined source components and so forth, right? Just based on where they are in this auxiliary DAG. Okay. Suppose magically I could pick that next vertex V to be from a sink component. Okay. And originally what I would do is I run DFS from V to get everyone V can reach, and then in reverse run it in a reverse graph to find anyone that can reach V. But if it's from the sink component, everyone V can reach is exactly the strongly connected component because it won't leave its component because it's a sink component. There's nowhere to go. So if I could pick a sink component, then instead of doing this SCC subroutine where I flip the graph and ultimately have to look at everything, I could just run DFS from V and only visit the vertices reachable from V. Right? So I'm in a sink component. I just explore down here, and that's my component, strongly connected component. Anyone V can reach it. If V is from the sink component, a sink component, and I can rip it out of the graph. We don't know yet how to get a vertex V from the sink component. Okay? But if I could, then I can make a strategy where just like before, I'm trying to get one strongly connected component at a time, but I always get a vertex V from the sink component. I just run DFS from V, and that's the strongly connected component that I rip out of the graph. No. A vertex V in the sink component. So if I ran DFS from V here, who would I visit? That's right. So DFS from here would mark off the entire strongly connected component for V. Yeah, so then what we do is we remove this. Okay? So I already found that vertex strongly connected component just by running DFS from that vertex because I chose the right vertex. And then I can rip it out of the graph. And we can keep going, right? Pick any vertex from a sink component in the remaining graph. Bottom right? Okay, so that's a sink component. I'll run DFS from there. It can't go anywhere, right? Anyone it can reach, which is only itself, that is a strongly connected component. I'm done with that vertex. Okay? Pick another vertex in a sink component. So to update this DAG, we've gotten rid of this, we've gotten rid of this. All right, the purple. So pick any vertex here, right? I'll pick this one. I run DFS, it's going to go here, it's going to go here, it's going to go here. Okay? All the vertices it visited are exactly the ones we highlighted in purple. I don't have to do this reverse thing because it's a sink component in the remaining graph. So there's nowhere to go outside of its component. Yeah, it is. So our bottom graph now looks like this. Yeah, no, we don't have the bottom graph. I'm just updating what it is. Yeah, we don't even have a full algorithm because we haven't figured out how to get these vertices, these ideal vertices. But if I could pick which vertex I wanted to next, which at this level feels like you know the answer to pick the answer, so it's a little cheating, I agree. But if you did, things are starting to get much faster. So I start erasing this because I've already figured this out, right? And now I pick any vertex in a sync component. Uh, Not true. You want to pick yellow because green can still reach yellow. So if you do yellow, then you're going to traverse like this, and you're going to traverse like this, right? And you're going to get those vertices, right? And you can't escape. And you get to erase all this, right? You figured out all the vertices in that component, and then you just pick one of these vertices and you're done, okay? Now, if you could get these vertices in the order you want, let's set that aside. I just give you this magical order. So in the best possible case, how long would all of this have taken? The running time. Just m plus n. We're actually only looking at every edge once because in the sync component, I search the whole sync component and I rip out everything I've searched, right? So I never look at the same edge twice, never look at the same vertex twice. Yeah. Ah, okay. So what if there was no sinks? Yeah, so can you have a DAG with no sinks? I have some vertex here. Okay, it's not a sink. It must have some edge going out, right? And it can't be a cycle, so I can't go back and visit. Okay, this vertex, it's not a sink. It must have some edge going out, but it can't be a cycle, so it has to be a new vertex. Oh, this vertex can't be a sink, so it must go out to a new vertex, right? At some point, you're going to run out of vertices. There's only n vertices, right? You can't continue this indefinitely. So you can't have a case where there's no sink. Otherwise, I would be able to keep finding another edge, another edge, another edge. Well, eventually, you're just going to keep peeling things off, right? So if I had some other vertex, like an extra vertex I added to the graph like this or something, that would be an example. We would have just done that last. By the end, it's going to be just sitting there by itself, and then we do DFS on that. Eventually, it'll become a sink. Everything will become a sink. As I delete things, there's always some sink. There's always at least one sink. Eventually, it itself will become a sink. Okay, good. Right on time, I think. Okay, so we only have to visit each vertex once if we do it in the right order, each edge once. Are we going to do topological sort? Yeah. Okay, so if we can figure out the sync components on the fly, we'd have a very good algorithm. Okay, but it's not clear, again, as you pointed out, it feels like we need to know the answer to get the... Okay, so how do we find the sync component ordering? Okay, so let's look at post-order DFS. Post DFS, or I don't know what I wrote there. I think it's post DFS order. Okay, so okay, and so if I ran post DFS, um, then I get some kind of ordering like this. Okay, now, okay, what's kind of interesting, or what do you guys notice about this? Ah, okay, is the first vertex from a sync component. So this is actually quite subtle. So you might think if I do post DFS order, the first vertex to get printed will be a sync. Okay, that's actually not quite true. But the last vertex to get printed will be from a source. And that will always be true. But let's see why. Okay, so, but that's true in this picture. In this picture, I was careful to make sure the first vertex is from that purple region. That was not a sync component. The second vertex is from a sync component. And but the green is a source component, and it did seem to come last, right? So, you know, all of the edges that go across components from different colors, they're going in the same direction. They're going right to left, right? And they're following this this component thing. Okay. Now the only messy part is that in the actual listing of the vertices, the vertices can be intermixed, right? You have purple, red, purple, purple. Okay, so not all lined up. But if you only focus on the edges going across colors, it does form something like this. Huh? Um, yeah, the original graph. I think this is accurate, but it's a little hard to tell. I'm just missing this edge. The vertex is from a source component, is what I meant to say. So this is just something printed out from DFS. This is just a printout of DFS. And if you look at the printout of DFS, the last vertex will be from a source component. And okay, so I guess this is maybe one way to state the lemma. If you ever, so this isn't quite a topological ordering in the sense that, if something is in a cycle with itself, there's no particular order amongst themselves. But every time I've listed the vertices so that if Vi can reach Vj, but Vj cannot reach Vi, so there's only a one direction, okay, then Vn is always going to be from a source component. Okay, so if my listing follow this rule, if Vi can reach Vj, but Vj cannot reach Vi, then I is going to be listed after Vj. I is going to be listed after J. Okay, so I can reach J, J cannot reach I. Then you're always going to have this order. If your listing follows this kind of rule, then whatever's at the beginning has to be from a source component. Okay. All right, so given this, right, how can I try to get a vertex from a sinc component? Yeah. Okay. So what we're going to do is we're going to reverse the graph and we're going to compute a post-DFS ordering. Okay? So it's going to put the sources of the reverse graph at the end. Source component, vertex from source component, which will be a sinc component in the input graph. Okay? So you reverse the graph and you do a post-order DFS. That gives you your first vertex V, whatever comes last. Then you do DFS from V, you rip it out. And you rip it out of your ordering. Okay? But you look at the remaining ordering and says, oh, it still obeys the same rules. It's a post-DFS ordering of the graph with those vertices ripped out. But it still has the property that if I can reach J, but J cannot reach I, then I will come after J. Okay? So even when you rip it out, your same ordering is still good. Otherwise, you have to recompute it, and that would be an issue, running time-wise. So you only have to do the ordering once and the reverse graph, and then you just read it from back to the beginning. Okay? Then you'll always be able to get vertices from the sinc component, and you'll miraculously get an m plus n time algorithm. Okay? I think that's all we have. All right, any questions? It's the most magical algorithm we'll see in this class. It's all coming from like being very careful about what the post-order DFS does and thinking about these things and just adding them together. Yeah, sounds good. All right, we'll end there. Ryan's here, I'm here, and see you guys next week.